The topic covered in this presentation is the Introduction to Data Analytics Applications. This content covers Chapter 3 of your course textbook. There are numerous categories for analytical applications, including data storage applications, such as databases, data warehouses, or data marts. Data analysis applications include those that can carry out statistical analyses, data mining, and data visualization. Also, there are data reporting applications that can support the creation of reports to summarize clinical, financial, and operational findings. Let's begin by looking closer at data storage applications. Data storage applications include software that is used to analyze and manage data. The purpose of the software is to facilitate accurate, efficient, and effective methods of analyzing data to create meaningful insights and directives. As healthcare data increases in volume, varies in type and complexity, there's a greater need to use software to effectively use data, and that is why such applications are increasingly important. The methods used to store data can be explained and carried out in several different ways. Databases are the foundational element of storing data and essentially required for other methods discussed. A database is any collection of data organized for storage, accessibility, and retrieval, used to support a transactional system typically. Data warehouses can be adopted to consolidate the contents of the database for supporting data analytics. Essentially, a data warehouse is a type of database that integrates copies of transaction data from disparate source systems and provisions them for analytical use. Lastly, a data mart is a sub-selection of a data warehouse built to serve a very specific purpose in order to boost end-user performance. Typically, they aggregate or create summary tables which may be delivered within a data mart. Given the basis that the database is the foundational component of data storage, we must ensure that we fully understand how a database works. Let's begin by looking at the parts of a database. At the very basic core, a database is a collection of data, and that data includes rows and columns. If you consider a spreadsheet of data from MS Excel as a representation of a very simple database, if we ask the question, what does a row represent? How would you answer that? What if I ask the question, what does a column represent? Let's look at the figure on the bottom of the slide. The rows in this example, shown on the left, represent a record. Each record is unique from the other records and includes a single observation. That record can have data on many different variables. Those variables are represented in the columns shown on the right. We see that each record has a record number, a name, address, city, and state. This format is the basic tenet of a database. Now let's examine two arrangements of data and ask yourself, what does each row and each column represent in the following database? In this example, we have two columns. We have a column for males and a column for females. Now let's take a moment to answer these three questions. What does each row represent? What does each column represent? And what do each of the numbers represent? Now, given these questions, you might be noticing that you're having some difficulty answering some of these questions. The rows in this example don't represent a single observation. An individual can't have data in both the female and the male columns. Also, the columns both represent the variable sex, but different factors of that variable of sex, males and females. Also, we have no idea what those numbers represent. We would need additional information to know this. This arrangement may seem favorable because it looks simple, but this really is not optimal for a database. Let's rearrange this same data and let's try it again. Again, I'm going to ask you those three questions. What if I ask you, what does each row represent? What about the columns? And what does each of those numbers represent? What does MF represent? It's a bit easier, right, to interpret this information. We can easily see that the rows represent a single person or observation. The first row is for an 18-year-old male. The second row is for a 42-year-old male, and so on. The columns are for data on age and sex. Under the age column, we know that each of the numbers is for the age of the person. And under the sex column, we know that M is for male and F is for female. Although this arrangement is much more complex, it has a lot more information and it's easier to read. This arrangement is also the preferred method for formatting a database. There are numerous types of databases that we need to be aware of. The first type is a simple flat file database, which can be considered a spreadsheet. This is what the spreadsheets in MS Excel represent. The problem with a flat file database is that there tends to be a lot of redundancy and duplication in the data. A hierarchical database is a tree-like database that has branches. The highest branch is called a parent, and that parent can split off into what is known as children. The type of relationship is that a parent can have many children, but a child can only have one parent. This is a restrictive type of database, and there is no flexibility for a relationship amongst children or for multiple parents of a child branch. A network database is similar to a hierarchical, except it can have many parents and children. A network can have numerous relationships between children and parents and offers a flexible and efficient storage of data. The challenge, however, with a network database is that this resulted in complex many-to-many relationships, which can cause confusion and redundancy in the data. The best solution to date is a relational database, which offers a way to store data so that there are unique fields called keys, which can be used to relate to keys in other tables. This allows for lower redundancy in the data and more efficient storage. In healthcare, relational databases have dominated. The reason is that they can be defined in terms of the relations of data, they can handle huge data sets, they can be accessed programmatically, they support multiple users, and they can be accessed and updated remotely. A database management system is software that handles the storage, retrieval, and updating of the data in a computer system. There are many platforms in production, some that are licensed and require a fee to use, including Oracle, Microsoft SQL Server, and IBM DB2. Others are open source or free tools, such as MySQL and PostgreSQL. Users interact with a database management system, otherwise known as DBMS, to execute modifications, additions, queries on a database. These methods are executed using a programming language called Structured Query Language, SQL. Let's watch this brief video, which will offer us an overview of SQL.
In a world where databases are present everywhere, where energy consumption is recorded in a database, where all financial information is stored in a database, as well as the number and duration of all phone calls, where inventories, transport information, and even entertainment bookings all require a database, where almost all websites are powered by a database, when getting the right information at the right time is critical for many businesses. One language is used to access all databases, and this language is SQL. You'd better know it.
I want to teach you how to use SQL and how to use it well.
SQL can seem very simple. Databases store tables that have a name and contain rows of related information. Each column stores one particular attribute. In this example, each row is a collection of facts about movies. SQL is the language that's used to store the information, to maintain it, and to retrieve it. If you want to retrieve some particular information from this table, it's very easy. You type select, followed by the names of the columns you want to retrieve, followed by from and the name of the table. A database can contain thousands of tables, followed by where and a condition that must be satisfied by the rows you want to get back. This condition can apply to a column that will not be returned. You run the query and you get a subset of the original table that's only composed of the values of the columns you requested for the rows you requested. Very easy, isn't it? Unfortunately, very often simple elementary operations can combine into something that's very complicated. That's exactly what happens with SQL, which is a very powerful language. You don't need to be a genius to write good SQL queries, but you really need to understand well the logic behind the language. Otherwise, you may end up writing queries that are very slow or which return wrong results, or both. In this course, I'll explain to you, point by point, how to use SQL well. Not simply the syntax, but the spirit of the language. And I'll build up slowly. But clear explanations are not all. In any domain, if you want to become good, you must practice, and practice a lot. This is why on the Konagora website, you can at any time pause the video and try what I've shown to you. Or try variations. And play around. Until you're certain you've really understood. The course is composed of 12 modules. The first 5 are free, and there's no registration required.
See you soon on Konagora.com.
When discussing a relational database, there are 3 main components we should be concerned with. First is the entities, which is the name of the table of the database. An entity is a thing with independent existence, such as a patient, diagnosis, medication, and so on. Next, we have an attribute. This is the name of a column or field within a table or entity. An attribute is kind of like an adjective and includes the facts about the entities. For example, the patient entity may include attributes for gender, state, year of birth, and so on. Finally, there are relations that exist between entities. These are like the verbs that capture how entities are related to one another. There may be 2 entities, one called patient, the other medication. The relationship between the two may be that a patient takes some medication. Other examples could be relationships between a patient entity and diagnosis entity. This relationship may be understood by the fact that a patient is issued a diagnosis. Finally, a relationship between the diagnosis and medication entities maybe that a diagnosis is treated with a medication. But if we were to try to understand the entities, attributes, and relationship using a picture, the result would be what is shown on the screen. This is called an entity relationship diagram. You'll see the boxes are titled medications, diagnosis, and patient. These are what we refer to as the entities. You can think of these entities as individual spreadsheets of data. Within each entity are attributes. The attributes are like the names of the columns of data within each spreadsheet. For instance, in the patient entity, we have the attributes patient ID, gender, year of birth, state, and practice ID. The symbols before each entity specify the type of entity. We will learn a bit more about this in a bit. But for reference, the little gold key by the attribute name, this signifies the primary key. The triangle signifies a foreign key if the triangle is red. A blue triangle signifies just a simple attribute. The relationships between the tables are understood by the lines drawn between the tables. You'll see a line is drawn between patient and medication, and patient and diagnosis and medications. These lines show that there are relationships between those tables. We will look at these relationships further as the type of relationship is understood through a rule called cardinality. The entity relationship diagram, otherwise known as ERD, was first popularized by Peter Chen in 1976. In Chen's original model, he developed symbols to represent each component of a database. A square was meant for an entity, a triangle for the relationship, and an oval for the attributes. Now shown here is the same ERD that was displayed previously, albeit slightly simplified. We see that the patient entity, signified by a square, has two attributes listed in the ovals, sex and state. The patient entity is related to the diagnosis entity in that the patient is issued a diagnosis. The diagnosis table has the attributes ICD-9, description, and year. The diagnosis table is related to the medication table in that the diagnosis is treated by the medication. The medication table has the attributes NDC, name, and dose. Lastly, the medication and patients table are related in that the patient takes the medication. Now, the degree of a relationship between entities varies depending on the entity types. A unary is a relationship that exists when the entities are of the same type. For instance, if there are different physicians that practice at the same clinic and have the same address, there's a unary relationship between the physicians. A binary is the most common degree of relationship. It exists when entities of two different types are related to each other. For instance, when a patient has one kind of diagnosis, this is a binary relationship. A ternary exists when entities of three different types are related to each other. For instance, a physician, equipment, and procedure entity types are related to each other with a ternary relationship because the physician uses equipment for a procedure. Cardinality is the type of relationship one table has with another table. There are three main types: many-to-many, one-to-many, and one-to-one. The most common type of relationship is a one-to-many, and we strive to avoid many-to-many and one-to-one relationships. For example, consider a database designed to keep track of hospital records, such as a database that could have many tables, like a doctor table with information about physicians, a patient table for medical subjects undergoing treatment, and a department table with an entry for each division of a hospital. In that model, there's a many-to-many relationship between the records in the doctor table and the records in the patient table, because doctors have many patients, and a patient, they may have several doctors. There's a one-to-many relationship between the department table and the doctor table, because each doctor may work for one department, but one department, they can have many doctors. In the database we created, there is only one-to-many relationships. One patient can have many medications. One patient can have many diagnoses. And one patient can have many medications. A one-to-one relationship exists when both entities of a table are related by one and only one instance of the other entity. Usually, we don't use these. The reason is that we can simply have just one large entity rather than split them into two. This helps to reduce redundancy. A one-to-many occurs when an entity is related to one or more instances of another entity. You can also state them as a many-to-one relationship. This is the most common type of relationship. A many-to-many relationship is very common in the real world, but not in a relational database. In fact, it is very bad practice to have many-to-many relationships. The solution, if there is a many-to-many, is to create a third intervening entity known as an intersection table to transform the many-to-many relationship into a one-to-many, many-to-one. I know, it can be a little confusing. These relationships are depicted with symbols on an entity relationship diagram. The symbols are drawn on the lines that connect the entities. The first one shown is the symbol for one and only one. The next is the symbol for one or many. Then we have the symbol for 0, 1, or many. Finally, the symbol for 0 or 1. To better understand these, why don't we look back at our ERD and see if we can interpret them. Here we see that the relationships between the patient table and diagnosis table is one to many, where one and only one patient is related to 0, 1, or many diagnoses. Also, there is a one-to-many relationship between patient and medications, where one and only one patient is equal to 0, 1, or many medications. Finally, there is a one-to-many relationship between diagnosis and medications, where 0 or 1 diagnosis is related to 0, 1, or many medications. Keys are incredibly important to a relational database. The keys are what link the entities based on the shared attributes of the relationships. There are two main keys we will discuss: primary and foreign keys. A primary key is an attribute that can uniquely identify a particular instance of an entity. There's only one primary key for an entity, and each entity must have a primary key. A primary key cannot be duplicated within a table. Consider the patient table for a moment. Do you think the following can be a primary key? The full name of a patient? Probably not, right? It's not a unique field. Different patients may have the same name. Social Security number. You may want to say yes, it could uniquely identify a patient, but what happens if the patient doesn't know their Social Security number? In fact, this results in common duplicate entries of the same Social Security number. Therefore, it might not be unique. What about medical record number? Well, maybe, if it's done so correctly. We'll learn more about the primary keys in our database. Foreign keys in one entity are a primary key in another entity. For instance, we may need to know what patient takes what medication. So the patient ID, which is the primary key in the patient's table, it's also present in the medications table. In the medications table, however, the patient ID is known as a foreign key. A foreign key can be duplicated in a table, and it may or may not be null, meaning blank. The foreign key is what creates the link between different entities to denote specific records. Let's look at the ERD from before. Can you identify what the circled attributes are? These are the primary keys, as they are the unique identifiers for each entity. We have patient ID in the patient table, we have the diagnosis ID in the diagnosis table, and the medication ID in the medications table. What are these? Well, these are the foreign keys. You can see that there are foreign keys in the medications and diagnosis table, but why aren't there any in the patients table? The reason is that the patients table does not have any instances of medications or diagnoses. Consider the one-to-many relationship. For each one patient, there may be many diagnoses and many medications. Therefore, in order to link the patient table with the other tables, we need to include the patient ID in the medications and the diagnosis tables. Anytime there is a one-to-many relationship, the many side of that relationship, that's where the foreign key lives. So what is the purpose of the keys? Well, the primary purpose is for organizing the data in a way to effectively navigate the data and understand what fields are related to one another. Let's actually look at a spreadsheet version of these tables to better understand. As you can see, this is the data in the patients table. Each row represents a single patient. In the first row, we have patient 1, who is male, born in 1956, and lives in Arizona. You'll note that the patient ID, which is the primary key, is not duplicated in the table. The diagnosis table has a diagnosis ID, which is the primary key, and it is not duplicated. However, patient ID is a foreign key, and we do see duplication. Why is this? Well, the reason is that one patient may have multiple diagnoses. Therefore, this same patient ID may appear in more than one row. You'll see patient ID 1 has 3 different diagnoses, while patient 2 has 5 diagnoses, and so on. One patient with multiple diagnoses may take multiple medications. Therefore, in the medication table, the same patient may appear in more than one row, and the same diagnosis may appear in more than one row. Yet, not every diagnosis gets a medication. Therefore, we may see that the diagnosis ID may appear in the diagnosis table, but that diagnosis ID never appears as a foreign key in the medication table. It's important to understand that without keys, we would not be able to link these tables. This begs the question, why not just use one big table for all of the data? Well, the reason is that since a patient can have multiple medications and multiple diagnoses, it's best to split these entities off in order to extract the most meaningful information. Imagine if all that data were stored in a single table. That single table would be huge. It is much more efficient to split the data up into individual entities. Now, to accompany a user in understanding how to navigate and understand entities and the attributes, a data dictionary offers a guide to the data. It helps users understand the meaning, the relationship, the origin, and the usage, as well as the format of the data in the database. So now that we have an understanding of data storage applications, let's actually look at data analytics applications. There are 3 main categories of data analytics applications. The first are statistical applications, which are used to examine differences in groups and identify relationships between variables. Examples of software include SPSS, SAS, and R. Another application suite includes data mining software, which are used to categorize variables and predict outcomes. Some examples of software include Weka, SAS Enterprise Miner, and R. Lastly, we have data visualization software, which is used to view trends. Examples include Tableau and ClickView. The purpose of statistical applications is to compare groups of data so that analysts can look for meaningful differences, relationships, and changes. This software can return descriptive statistics, which summarize the basic features of the data in a study. For example, the mean, the median, the mode, and standard deviation. Also, the software can run inferential statistics, which are methods to make judgments of the probability that an observed difference or relationship between the groups is significant. Examples include t-tests, linear regressions, and ANOVA. Some ways statistics can be used is to use a test to run a comparison of the average length of stay for all inpatient stays at Hospital A to all inpatient stays at Hospital B. In this example, a two-sample t-test can be used to determine if the average length of stay is significantly different between Hospital A and Hospital B. Data mining applications provide a solution to create a process of discovering patterns in large data sets using algorithms that are adapted from artificial intelligence, machine learning, statistics, as well as database systems. There are two main categories of data mining algorithms. These include supervised and unsupervised learning. In supervised learning, a user creates a model from historical data to predict an outcome. Examples of some models include decision trees, random forests, and neural networks. In unsupervised learning, a user creates a model from historical data to categorize data into groups. Some examples include k-means clustering and hierarchical clustering. An example of a data mining method is the use of historical data on breast tumor masses to predict if the tumor is benign or malignant. The historical data includes features of the breast mass, such as radius, texture, perimeter, area, etc. In the historical data, it is known whether the tumor is benign or malignant. And using this historical data, a data mining model can be applied to find the features that best predict malignancy. For instance, a decision tree may be applied. In this example, we can see that the decision tree creates rules to predict malignancy or benign tumors. Let's follow this to a few branches. So if we look at the first rule, if the worst parameter is greater than 105.95 millimeters, and the worst concave points are greater than 0.15 millimeters, what we see is that 100% of the time the tumor is malignant in this group. Now, if the perimeter is less than 105.95 millimeters, and the worst concave points are less than 0.16 millimeters, 100% of the time, the tumor is benign. Now, this model that was created can be implemented on new data that does not include whether a tumor is benign or malignant. This may help to determine if the tumor is suspected to be benign or malignant. Now, from our data mining model, if all were classified as malignant, we would have an error rate of 36.7%. However, in our model we created, when we assess the quality of the model, we see that the error rate is just 7.1%. Therefore, our model performs better than just random. It may appropriately help to predict breast mass malignancy. Data visualization is our last type of analysis, and the purpose is to assist in understanding the significance of data and trends by placing it in a visual context. Data visualization is commonly adopted for creating dashboards, which create real-time analyses using graphs and tables. Reports can also incorporate data visualization methods to create analyses that are completed frequently and summarize the data using graphs and tables. Here's an example of a dashboard that uses data visualization methods. This is from the Hospital Compare website to compare hospital performance based on various metrics. In this example, we are comparing heart failure readmissions across 3 hospitals in Chicago, Illinois. We see that Rush University Medical Center has the highest heart failure readmission rate, followed by Mercy Hospital, and Mount Sinai Hospital has the lowest of the 3. The national rate is 21.9%, and all hospitals exceed this value. These types of applications have value for supporting a variety of analytics, including clinical, financial, and operational analytics. In clinical analytics, the intent is to evaluate clinical outcomes. The type of analysis can vary depending on the data, the user, or the clinical action. The data that is used may be retrospective in nature or prospective, where it is actively being collected. Performance measures can often be categorized based on whether they analyze an input to the care process or an output of the care process. There are very common different types of performance measures, including things such as the cost, resource, and efficiency measures that track the specific resources used. For instance, how often CAT scans are used, or how often certain drugs or surgical procedures are used, and the rates at which these resources are consumed, as well as the payments and costs for healthcare services. These are common performance measures. Others may be structural measures, which provide information about how the care delivery system operates. For instance, the volume of specific surgical procedures performed by a physician, or the percent of prescriptions transmitted electronically. The National Quality Forum, NQF, has established a consensus process for endorsing clinical performance measures, and they provide an online catalog of the measure definitions. In financial analytics, the intent is to evaluate financial impact. This type of analysis is often incorporated into a monthly or quarterly report. In fact, some organizations have a financial dashboard. A financial analysis often includes information on financial performance related to charges, the contribution in total margin, reimbursement, the variable in total cost, the length of stay, and case mix index. Operational analytics uses data to improve the performance and efficiency of an organization. It often includes analytics to optimize use of expensive resources, to improve access for patients, and to cut wait times. In conclusion, various applications are available to obtain data and carry out a variety of analytical procedures. It's important to emphasize that a strong understanding of the applications and data is required to be successful in data analytics.